Hello! There is one final way we can use the central limit theorem and the normal distribution that we have learned about this week, and that is in the calculation of confidence limits. As we have discussed in previous weeks, confidence limits come about when we share the results we have obtained from our experiments with our colleagues. For instance, when Alice tells Bob about the results she got from her experiments, she doesn't simply tell Bob the average result. Instead, she states that 90% of the results were between 3.5 and 5.5. It is only because Alice has quoted her confidence limits that Bob can determine that if the result he obtained by doing what he thinks is the same experiment as Alice is consistent with what Alice observed. In previous weeks, we obtained these confidence limits by resampling. In doing so, we wrote a function to generate a sample mean from n random variables like the one shown here. This function was then called multiple times by using commands like the one shown here. The confidence limits were then calculated by taking suitable percentiles from the distribution of values contained in the NumPy array called samples. Now suppose that we try to do something similar to what is coded here in a real experiment. Each mean that I have computed was calculated from 1,000 random variables. I then generated 100 means. I would thus have to do 100,000 experiments to generate this data. This is not really feasible, and so a cheaper method than resampling has to be determined. To see how this cheaper method might work, recall that the mean function that is calculated here is calculating the formula that is shown at the top of the slide. In this expression, each of the xi is a random variable with expectation mu and variance sigma squared. More importantly, by the central limit theorem, the sample mean here is approximately a continuous normal random variable with the parameters shown here. This is important. The central limit theorem tells us the distribution that we are sampling from when we generate a sample mean. We thus no longer need to resample this variable. We can instead simply use the information on the distribution that we know from the central limit theorem. The code shown on this slide shows a part of how this works in practice. This bit of code should be familiar. We have sampled a uniform random variable multiple times, and we have computed a sample mean and a sample variance. We have discussed this code like this at length in previous weeks, so we'll not dwell too much on what this code is doing. I would just note, however, that the sample variance that we have computed is an estimator for the variance of xi. In other words, this is an estimator for the variance of the random variable. It is not an estimator for the variance of the sample mean. To estimate the variance of the sample mean, we have to divide this estimate var by n. Var x bar here is thus our estimate for the variance of the sample mean. Now, because we know that the sample mean is approximately normally distributed, we no longer need to resample to determine the percentiles. We can instead calculate the 5th and 95th percentiles for the distribution using the following code. This modification reduces the expense of the procedure considerably. Because we no longer need to resample, we can achieve what was achieved on the previous slide with 100,000 experiments with only 1,000 experiments. Having established that we can reduce the expense, you are perhaps wondering where the code that we have used to determine the percentiles come from. Let's thus take a moment to discuss what this SciPy stats norm ppf function is doing. Before we get onto that, consider the probability density function for the standard normal random variable that is plotted here. A normal random variable is said to be standard if the mu parameter is 0 and the sigma parameter is 1. The probability density function for a standard normal random variable is thus the expression shown here. As you know, we can get the cumulative probability distribution function by integrating the probability density function using the expression shown at the bottom of the slide. The cumulative probability distribution function for the standard normal random variable looks like the graph shown on the right here. This function is often called the error function. There is no particularly simple way that we could write this function. We just have to write it as the integral of the PDF. So we write this using the expression shown here. Now that we have introduced the error function, we are in a position to understand the Python command that was introduced on the previous slide. Let's suppose that we call SciPy stats norm ppf with the argument 0.6. This command tells Python to look for the value of x for which the error function is equal to 0.6, as is illustrated here. In other words, if we call the error function capital Phi of x, then SciPy stats norm ppf is just the inverse of this function, as shown here, i.e. it's the inverse of the error function. SciPy stats norm ppf, in terms of confidence limits, thus allows us to say that 60% of the random variables we draw from a standard normal distribution will be less than or equal to SciPy stats norm pf 0.6. In other words, this serves the same purpose as the NP percentiles function that we have used in previous exercises. That is all well and good, but in the code on the previous slide, we were not drawing random variables from a standard normal distribution, as the mu parameter of the distribution was not 0 and the sigma parameter was not 0. How then do we make this connection? How do we draw these percentiles for distributions, for normal distributions that are not standard? Well, let's suppose that we want to calculate the cumulative probability distribution function for the normal distribution. This cumulative probability distribution is given by the integral shown here. This integral can be solved by substitution. In particular, we will use the substitution z equals y minus mu all over sigma. To do this definite integral by substitution, we need to change three things. The first thing we need to change is the integrand, which must be written in terms of z rather than y. Y minus mu all squared over 2 sigma squared is equal to z squared over 2. So the e to the minus y minus mu all squared over 2 sigma squared in the current integrand will become e to the minus z squared over 2. The second change that we need to make is that we need to change the infinitesimal, i.e. the dy. To change the infinitesimal, we note that dz by dy is equal to 1 divided by sigma. We can thus write that dy is equal to sigma dz. The final thing we need to change are the limits. The lower limit is no problem, as z is equal to minus infinity when y is equal to minus infinity. For the upper limit, however, we must rewrite this as x minus mu over sigma. We thus arrive at the following integral. Notice that the factors of sigma in the numerator and denominator have cancelled here. Furthermore, the integrand that appears in this expression is the same as the integrand for the error function. So, what we are doing here is evaluating the cumulative probability distribution function for a standard normal random variable. We can thus use the expression that we arrived at on the previous slide and the symbol that we arrived at there, capital phi, to write this integral in terms of the cumulative probability distribution function for a standard normal random variable, i.e. the error function, capital phi. Now notice that we can rearrange this expression as shown here. We thus arrive at the following expression for the pth percentile of the distribution. This expression is written in terms of the inverse of the error function. The inverse of the error function being phi to the minus 1. This is the expression that is the basis of the expression for the percentile that I wrote on the previous slide. In other words, this is what is being evaluated when we use the expression shown, the Python that is shown here. To summarize then, we have introduced a cheap method for determining confidence limits on averages. To use this method, we estimate the sample mean and sample variance from our experimental results using the expressions shown here. We then note that by the central limit theorem, the sample mean is a sample from a normal distribution with an expectation equal to x bar and a variance equal to s squared divided by n. Given that we know the distribution for the sample mean, which is a random variable, we can thus calculate the pth percentile using the expression shown here. Except in special circumstances, which are not really covered in this course, this is our preferred method for calculating confidence limits, as it is much cheaper than resampling. Thanks for your attention, and good luck with the exercises that follow.